Okay, in section 3, we're going to be finding the value of trigonometric function values for some special angles. Namely, the angles we're going to look at are 30, 45, and 60. So the goal is to be able to find the values of these. So example, what's the sine of 30 without typing it in our calculator, and finding what's called the exact value. So all of our things in a calculator are approximations because they're decimals. So we're going to try to find the exact values of these special angles. Now everything we really do for this section, and for that matter of fact the next one, is based on these two special right triangles. If you recall these from geometry, we have two special right triangles. One is the 45, 45, 90. This is what's called an isosceles right triangle because two of the sides are the same, and then one is longer, the hypotenuse. And then a 30, 60, 90 triangle, which has sides in ratio of 1, square root of 3, and 2. So the side across from the 30 is 1, the side across from the 60 is square root of 3, and the hypotenuse is 2. So if we use these two triangles, we can actually find all of our trigonometric ratios from these triangles. So the first one we'll look at is 30 degrees. So we'll try to find the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent of 30 degrees. Well, if we think of 30 degrees as our angle, well then this side of this special right triangle is still the hypotenuse, but this will make this side the opposite side because again it's across from the 30 and this one the adjacent. When we do the 60, we'll switch it. But right now there's the opposite, there's the adjacent. So since the sine of 30 degrees is the opposite over the hypotenuse, it's 1 over 2. So what we know right away is the sine of 30 degrees equals 1/2. The cosine of 30 degrees is the adjacent over the hypotenuse. So in this case, that would be the square root of 3 over 2. And again, that's the cosine of 30 degrees. So we'll just kind of fill out this chart. The tangent is opposite over adjacent. So opposite over adjacent is 1 over the square root of 3. And if I wanted to simplify that by multiplying top and bottom by square root of 3, I certainly could. Square root of 3 over 3. And now the last three we just flip. So for cosecant, I flip sine. So instead of 1 over 2, it's 2 over 1, or just 2. For secant, it's the flip of square root of 3 over 2, or 2 over the square root of 3. Or if I clean that up by multiplying by top and bottom by square root of 3, it's 2 square root of 3 over 3. And the cotangent is just the flip of 1 over the square root of 3, or square root of 3. So if I do the 60, let's just do the 60 while we're here, then we'll do the 45. For the 60, everything is basically the same. This is still the hypotenuse, but this is now the opposite side, because from 60, this is the opposite. So again, it's all about what angle you're coming from, what's opposite, what's adjacent. So now we use these red sides for opposite and hypotenuse and adjacent. So the sine of 60 is opposite over hypotenuse. So in this case, that's square root of 3 over 2. So that's what cosine used to be for 30, now it's sine, because we switched opposite and adjacent. So for cosine, adjacent over hypotenuse is going to be 1/2. And for tangent, it is opposite over adjacent, which is square root of 3 over 1. Or just square root of 3. And again, for the rest of these, I can just start flipping them. So for cosecant, it's 2 over square root of 3, or 2 square root of 3 over 3. For secant, it's 2 over 1. And for cotangent, you flip it, you get 1 over square root of 3, or square root of 3 over 3. So the last one we'll talk about is the 45. So the 45, we'll have to use this other triangle over here, this other special right triangle that we have from geometry. And there's two 45-degree angles, so it doesn't particularly matter which one you pick. I'll pick this one to deal with, because that'll make this the opposite side, This is the hypotenuse, of course, and this is the adjacent. The nice thing in this case, you notice the opposite and adjacent are the same. This is the only triangle, the only angle that does this. So if we think of the sine of 45 would be the opposite over hypotenuse. This is 1 over square root of 2, which is sometimes also simplified by multiplying top and bottom by root 2, and you get square root of 2 over 2. The cosine is the same, so it's 1 over the square root of 2, which is square root of 2 over 2. So the sine and the cosine for 45 are the exact same. Tangents opposite over adjacent, so that's 1 over 1, which is 1. And again, the rest of them I can just flip. So if I flip 1 over square root of 2, I get square root of 2. Same for the secant. And if I flip 1, I get 1. So these are the exact values for all trig functions of a 30, 45, or 60 degree angle. And we will actually use these to find some bigger angles later on. So we know we can find some expression values for these. So for example, sine 45 times cosine 45 is square root of 2 over 2 times square root of 2 over 2. Square root of 2 times square root of 2 is square root of 4 over 4. But the square root of 4 is 2. So we get 2 over 4, which is simply 1/2. Let's look at evaluating another one. This one says secant squared of 45 divided by tangent of 60. So I know the secant of 45 is square root of 2. So this is square root of 2, but then it says squared, which goes there. You'll notice when we square a value for a trig function, we typically put it after the thing before the angle. So that's kind of a typical notation. Divided by the secant, the tangent of 60. And the tangent of 60 from our unit circle is the square root of 3. So if I take the square root of anything squared, that just gives me the number. So this is 2 over the square root of 3, which I can simplify, or I can just keep it like that. I could get rid of the radical denominator, but I'm just going to keep it like this. So this one says the tangent of 45 plus the cosine of 30. So again, I can replace these because I know the angle from our exact values on the first page. The tangent of 45 is just simply 1. And the cosine of 30 is the square root of 3 over 2. Now if I wanted to put there's not much you can do because this has a root and this doesn't. The only thing I could do is I could write this as 2 over 2, make them with common denominators. So sometimes people would write them as 2 plus the square root of 3 all over 2. Even though you're really not putting them together, you're just putting them over a common denominator. It's sometimes written like that. Very similar to like a solution of a quadratic formula. Okay, our last one we have here is 7 cosecant of 30. Now the cosecant of 30 is 2, so this would be 7 times 2, because again, from our chart before, cosecant of 30 is 2, minus the square root of 3 times the cosecant of 60, and the cosecant of 60 is also 2. Or pardon me, the cosecant of 60 is 2 over the square root of 3. So if you look here, these will cancel. So this gives me 7 times 2, which is 14, minus 2. 14 minus 2 is 12. So even though we've got these weird square roots and all these kind of irrational numbers, sometimes it works out to be real nice. Okay, so far we've only dealt with those 3 angles, and we've dealt mostly with acute angles, but we're actually going to talk about angles that could be actually bigger than 90. We're actually going to talk about any kind of angle, because angles, as we know them, usually between 0 and 180, maybe 0 and 360. But really, you can have an angle that is any size. It could be positive, it could be negative. You can have really any angle you want. And then we'll also talk about a different way to measure angles, which is what's called radian measure. So the way we get any angle is what we use is called standard position angle. So a standard position angle is an angle in the XY plane with one side on the x-axis, on the positive x-axis, and a vertex at the origin. Or at 0, 0. Okay? So we're actually going to start graphing angles on our XY plane. So here is a XY plane, XY. So if I have an angle, I want to start the angle here. It's at this origin. I want to put one side right here along the positive x-axis. And then I'll put the other side, I don't know, somewhere else. So this angle could actually go two ways. We could actually have this angle where it starts here and goes here. Or this angle could start here and it could go here. So you actually have angles that could go two different directions. So we give names to these two sides in standard position. We call them initial and terminal. So initial is basically kind of the starting side, or the starting ray. And the initial side is always along the positive x-axis. And then we have the terminal side, which we call the ending ray. So if you think of them together, then this would be the initial over here, and this would be the terminal. Now, since we have these two directions moving, you're going two ways, one's going kind of in this upward direction, one's kind of going backwards, we actually denote those as positive and negative angle measures. So positive angles are angles that are going to rotate counterclockwise. So they kind of go up. So this red one here, this one right here, I'll retrace it. This is a positive angle measure. While negative angle measures will rotate clockwise. So they'll go the traditional way of a clock. So I can use this information to graph a couple angles. So a 172 degree angle is really big. Bigger than a 90, obviously. So if I'm going to graph this in standard position, I first start the first ray, the initial side, along the positive x-axis. And it's positive, so it's going to rotate in an upwards direction. So 172 degrees would rotate not quite here, because we know that two quadrants, this would be 180. So somewhere about here, this would be 172 degrees. So in theory, these angles could actually be bigger than 360, because you could just make a couple turns and you can eventually get past 360. So the second one says negative 300. I'll still start the same way. I always start on this positive x-axis. But in this case, I'll go negative, so I'll start going down. And again, I just denote the way it's going by this little semicircle. So there's 90, there's 180, there's 270. So really I need to just go about 30 more, so somewhere about there. So there is my terminal side. So you'll notice it says name which quadrant the angle lies in. When we say that, we just basically say what angle does it end up in. So this one ends up in 1, and this one ends up in 2. So using standard position angles, we can really talk about any kind of angle we want. As big as we want, as small as we want. So another way we can measure angles besides the typical degree measure is we can use what is called radian measure. It's kind of a new kind of way to measure angles, and instead of using degrees, it's actually measured in terms of a distance. So the way we do it is if I want to measure anything in radians, then it is basically this arc length is compared to this radius in some angle. So if I have an angle, let's say I have this angle, say it looks like 45 degrees. So if I go out, say 2 inches on this ray and 2 inches on this ray, then the movement will make some arc length, okay, whatever that is. Let's say it's 3 inches. Well, the radian measure wants to know how many radii, so how many 2's are in 3. So if this was our angle theta here, where we have an arc length of 2 and a radius of 3, then theta would simply be 3 over 2, which is 1.5. So ironically, a lot of these kind of radian measures will involve pi, and we'll see how that works here on the next page. So in this example you have here, you can see that this angle that we've created has a radius r and an arc length of r. So if I want to know what theta is in radians, it's r divided by r, which is 1. So in this case, theta is 1 radian. Now 1 radian in a conversion to degrees is about 57 degrees. So you can see, seems kind of appropriate for the angle we have there. So again, the radian measure is how many radii are in the arc length. So if we look at this example, we want to know what theta is. We want to know what the angle theta is. Well, it says the arc length is 8.7 and the radius is 4. So the angle measured in radians would be how many 4's are there in 8.7. So 8.7 divided by 4 will give us the radian measure of that angle. In this case, that's 2.175, and that would be radians. Again, it's not going to be in degrees, it's going to be in this new radians. Now, all the formal definition of radian measure it's kind of tricky for sure. So what we try to do is we try to make an easier way that we can convert between radians and degrees and vice versa. So if we have something in radians, maybe we want to use something more familiar like degrees. Or if we have it in degrees and we put it in radians for some reason, we want to be able to do that too. So there are 2 very easy conversion formulas for that. If I want to go from degrees to radians, I multiply by pi over 180. If I want to go from radians to degrees, I multiply by 180 over pi. Now the proof of this is actually really simple, so we'll prove it real quickly. So I'll start with a circle, full circle. Hopefully you remember from geometry, if I start here and go all the way around, that makes 360 degrees. A full circle is 360 degrees. We'll start with that in our proof. But if I do this in radians, let's say I do this circle and I have it radius r. Well, then the distance around this angle, all the way around, is the circumference of the circle, which is 2 pi r. So the arc length is 2 pi r. So our angle in radian measures is 2 pi r divided by r, which is 2 pi. So what this says is 360 degrees equals 2 pi radians. So we can divide those both by 2, and that would say 180 degrees equals pi radians. So let's look at how we would convert a couple of these angles between the two types of measures. So first we'll start with degrees. So if I'm going degrees to radians, I'm going to multiply by pi over 180. So what we typically do in these is I don't mess with the pi's. So my answer, I'm going to have a pi in it. So what I'm going to simply do is reduce the fraction 200 over 180, which is 20 over 18, which is 10 over 9. So this angle would be 10 pi over 9. And again, that's just simplifying the fraction 200 over 180 and adding a pi on. So 200 degrees we would say is 10 pi over 9 radians. Same thing for 120 degrees if I multiply by 180 or pi over 180. So this will have a pi in it. So if I simplify 120 over 180, that would give me 2/3. So this would be negative 2 pi over 3. So last one, same thing, pi over 180. I'll simplify this fraction. So you can put 17.25 over 180 in the calculator to simplify it, but this is going to simplify to negative 23 over 240, and then with our pi in it. Now going the other way could be a little messier, especially if your angle does not have a pi in it, because we're going to multiply by 180 over pi. 180 degrees over pi radians. So what we'll do is we'll multiply the tops and then divide by pi. So 180 times 3.14, or pardon me, 1.63 times 180 divided by 3.14. This one's going to give me 93.4 degrees. So you can see how really small radian measures like 1.63 give us really big degree measures. If we do 2 pi over 7, we're multiplying by 180 over pi. Well, it's nice if there's a pi already there because the pi's can cancel out. So I'll also have 2 times 180 divided by 7. So that's 360 divided by 7, which is 51.4 degrees. And again, all these operations can be done in your calculator. I'm just kind of doing them on the fly. Same thing for this, 180 over pi. No pi's to cancel, so I'll multiply the tops. 32 times 180 divided by 3.14. This is going to give me a huge angle, 1834, negative 1834.4 degrees. So radian measure, just for now, a real brief introduction to what it is. In future coursework, you might encounter a lot of radian measure in physics and kind of conceptual classes like that. Used quite often because it really makes calculations much nicer than does our traditional degrees. So that is all for 8.3. Please let us know if you have questions that we can help you with.